Hello and welcome to my talk. I'm Michael Will from the RPTU Kaiserslautern Landau, and I'm presenting this work done in collaboration with the Lowndes Berkeley National Lab called ExTreeM, Scalable Augmented Merge Tree Computation via Extremum graphs. First I'm going a bit over the motivation, then I'm presenting ExTreeM step by step and going over the results we have seen. Merge trees are fundamental data abstractions of scalar field topology that record at which scalar values superlevel components appear and merge, and they have proven to support a plethora of visualization and analysis tasks since they effectively abstract complex datasets. They show the inherent structure of the dataset and characterize features, but for ever-growing datasets, the computation of those merge trees needs to be further accelerated. Two examples, we have a CT scan of bones with the density as the scalar value and a fluid mixing simulation with the entropy as the scalar value. The merge tree leaf segmentation effectively characterizes the different bones of the feet and the hills of higher entropy. And faster merge trees allow interactive topological data analysis of larger datasets on common workstations. We describe ExTreeM, a generic computation scheme using Extremum graphs to accelerate the computation of the merge trees. As the input of ExTreeM, we get a piecewise linear scalar field defined on a connected simplicial complex. We then use path compression to compute the ascending and descending manifold, which assigns to each vertex of the domain for the descending manifold the maximum that would be reached by following the gradient of the scalar field along the steepest ascent. Using this, we can efficiently identify critical points, and then we can build up the Extremum graph by connecting saddles to the maxima and minima which are reachable through the manifolds of the neighborhood and connecting the global minima and maxima. We have proven that the merge tree of the scalar field and of the Extremum graphs are equivalent, but the Extremum graphs are in general orders of magnitude smaller. Further on, I'm going to be focusing on the split tree containing the maxima and the split saddles. The joint tree can be done symmetrically. Theoretically, we can use any algorithm on the Extremum graph itself, but we even present a specialized merge tree algorithm on the Extremum graphs. If wished, afterwards, post-processing procedure can derive the merge tree augmentation that assigns each vertex to an edge of the merge tree. First, for the descending manifold, we use path compression, where initially each vertex points to the largest neighbor and the maxima point to themselves. Then, iteratively, in each step, we replace the pointer of a vertex with the pointer of the pointer, and we repeat until all pointers converge to the maximum. In worst case, this may need as many iterations as the longest path, but in practice and through parallelization, it effectively doubles the path length in each step and needs few iterations. For the critical point computation, we can see that the critical points are characterized by the connectivity of their upper and their lower link. For the split, we care about the upper link. And we can also optimizably see that a vertex can only be a split or merge saddle if its upper link vertices lead to at least two distinct maxima through a monotone path. And this is already recorded in the descending manifold and can effectively just be seen there instantly. We can also see that the neighbors of interior vertices of regular grids can be consistently enumerated and interpreted as a binary number, with the ith bit representing whether the ith neighbor is part of the upper link. And this binary number can then be interpreted as an address index in the lookup table that records if, for this setting, the upper link is connected or not, also leading to further optimization. Now that we have the critical points and the descending manifold, computing the Extremum graph is straightforward. From every saddle, we can add an edge between the saddle and the reachable maxima of the upper link. and we only store the outgoing edges from the saddles and can therefore log-free parallelize it. Theoretically, one could apply any merge tree algorithm on the Extremum graph, but we introduce Extremum graph pairing, which uses the structure of the Extremum graph for further acceleration. One can see that some edges in the Extremum graph correspond to persistence pairs and therefore branch endpoints of the merge tree. These are exactly the edges MS, where M is the smallest reachable maximum of S, and S is the largest reachable saddle of M. After we find these, we can topologically simplify the graph and continue until we're done. And the simplification is, okay, we connect the saddle with the smallest maximum, and we save a pointer to replace the smallest maximum everywhere with the largest maximum reachable by the saddle. We have to do a path compression on this complete pointer because we may actually point to a paired maximum. For example, M2 and S2. M2 is the smallest maximum reachable by S2. S2 is the largest saddle reachable by M2. Therefore, they are paired, and every occurrence of M2 now points to M3, which is the largest reachable saddle by S2. But M3 is already paired with S3, so we have to basically path compress this again so that afterwards M2 points to M4. We continue until we at the end S1 is paired with M0, and the only points left over are M4, which is the global maximum, and R, which is the global minimum, and then we connect those. Afterwards, for the augmentation, we first use the descending manifold to find a maximum to which the current vertex ascends. Then we can walk down the merge tree branches until the last vertex of a branch is smaller than the current vertex. This shows us a general region where we're in, and in this region we can use binary search to find the correct saddle. We have compared ourselves to parallel peak pruning and to FTM tree, which is the current reference implementation in TTK. We couldn't run all our datasets on FTM tree because of memory constraints, but we have seen that we are up to 1 order of magnitude faster than parallel peak pruning and up to 2 orders of magnitude faster than FTM tree. One can see that we depend on the size of the Extremum graph, which is seen in percentages under the datasets. For example, for the JET in cross-flow dataset, where the Extremum graph is only 0.03% of the whole domain, we have our best speedup. Well, like Perlin noise, where most of the points are critical points and the Extremum graph is very large, we still have a speedup, but not as substantial. Our main contributions are the generic merge tree computation scheme ExTreeM and the novel merge tree algorithm Extremum graph pairing with a high parallel efficiency and a low memory footprint. And we also provide an open source implementation in the topology toolkit. Should be integrated into the main TTK branch by the time this conference runs. For the future work, we are looking into adapting the generic concept of ExTreeM with other merge tree algorithms instead of Extremum graph pairing. For example, triplet merge trees or parallel peak pruning, and combining the strengths of all of them. We're also looking into adapting ExTreeM for the GPU and for distributed versions to further make use of further parallelization. Thank you for your